Welcome. Today we'll be reviewing second-order ordinary differential equations. We'll review reduction of order procedure. So that's when you know one solution to the differential equation and you can find another solution. We'll look at homogeneous second-order differential equations that have constant coefficients, and then we'll look at non-homogeneous second-order differential equations, certain non-homogeneous equations with constant coefficients, and we'll look at the method of undetermined coefficients to find a particular solution. Okay, so second-order ODE, ordinary differential equation, generally might look something like this. P of x, so some function, so x is the independent variable, and second order means that an unknown function y is involved and up through its second derivative. Some function of the independent variable times y prime, some function of the independent variable times r times y, and that's equal to the right-hand side. There's generally some function here of the independent variable. Okay. By constant coefficients, we mean that these functions of x are just constants. So we have this is constant coefficients. Okay. Furthermore, if g of x, the right-hand side, is equal to 0, then we say that we have a homogeneous differential equation. So homogeneous in this context means the right-hand side is 0. Okay. So first we'll look at this procedure of reduction of order. Okay. So this is where you have the homogeneous differential equation, and I'm gonna write it in this conventional form where we go ahead and divide everything by the function of x that multiplies y double prime, so that we can write this as y double prime, and I'll write this as lowercase p of x times y prime plus lowercase q of x times y. Okay, and that's going to be homogeneous. So I'm going to look at differential equation of this form, and the idea is that you're given a certain one solution to the differential equation, and so this is a solution that's known. It's a known function, and what we want is y2, which is a second. It's another, but linearly independent solution to the same equation, same homogeneous equation. Okay, and I'll derive the formula, but first I'll just give you the formula. Okay, so what we assume is that the second solution is equal to some function of the independent variable times the first solution. So for the shorthand, I'll just write that as u times y1. So the second independent solution is some function u of the independent variable times y1, which is the first given solution to the equation. Okay. And then there's a formula for finding this u, which we will derive, but so this formula actually involves two integrals. Okay, so once you write your differential equation in the standard form, where the coefficient for y double prime is just 1, you identify p, this function right here, multiplying y prime, and then you're going to take the negative of that and anti-differentiate. And that's going to be the exponential of the antiderivative. You divide by the first given solution squared, and you anti-differentiate again. That gives you u. And once you know u, you just multiply the first given solution to get the second linearly independent solution. And you can prove using the Vronsky that this would, y2 would indeed be linearly independent from y1. Okay. So let's just go through the mechanics of this procedure first with a problem, and then backtrack and try to derive this formula. Okay. So here's an example of using reduction of order. Okay. So we're going to take the second order ordinary differential equation with constant coefficients. It's homogeneous, the right hand side is 0. And I want to give you that one of the solutions to this equation is e to the 3x. So x is our independent variable. And we want to find a second solution. That's going to take the form of u, which is some function of x, unknown function of x, times y1, right? The first solution. And I'm just going to, for right now, I'm just going to use the formula for what gives us a valid u. So here, the differential equation is already in this kind of conventional form, where the coefficient for y double prime is 1. So identify p of x is simply this number, this multiplying y prime. So the negative of p and we anti-differentiate to get 6x. I'm just trying to find some function that works, so I'm going to ignore the constant of integration, even though I didn't have to. Okay. And then once we have that, right, so the result of the negative of the antiderivative of p of x is 6x. Then we divide by y1 squared. And anti-differentiate. So we get that u is equal to x. So now we have the second linearly independent solution. U times y1 becomes x times, well, what was y1? It was e to the 3x. Okay. And I'll quickly confirm that these are independent solutions by computing the Wronskian of y1 and y2 at x. So that's the determinant of y1 prime, y1, y2, and then its derivatives. Okay, so let's recall y1 is e to the 3x, y2 is x e to the 3x. So y1 times y2 prime. So I guess I need to use product rule. Minus y1 prime times y2. Okay. So these cancel, and we see that our Wronskian is an exponential function of x. So since this Wronskian is always positive, in particular it's never zero, then we indeed have that y1 and y2 are independent on the whole number line for all x's. Okay. Okay. So let's just take a look at that example. We were given a solution to this homogeneous equation. We assumed a form for it, and we use this formula to find the function that should multiply y1 to give us a second linearly independent solution. And we confirmed using the Wronskian, since the Wronskian was non-zero on the whole number, that y1 and y2 are indeed independent solutions on the number line. So what we will do next is actually derive this formula for u. Okay. So we're going to have a second order equation here, written in a conventional form. And reduction of order works to find a second linearly independent solution for a homogeneous equation, so the right-hand side is 0. Okay, so we are given y1 as a solution to the equation. So in particular, we know that if you differentiate y1 once, twice, plug it into the differential equation, you would get 0, because this is a solution. Okay, now we're going to assume that we can find a second solution that is given by some function of the independent variable times the first solution, the first given solution. And if we want to figure out what u would be sufficient here, well, let's just differentiate y2 once using product rule, and twice, again, product rule. So differentiate the first term using product rule. That came from differentiating that. Plus, and now differentiate the second term using product rule. So that came from differentiating that. Okay. And of course, we see that the two middle terms are like. Okay. So now we're going to take y2 and its derivatives and plug it into the original equation here, right? Okay. So you get y double prime I forgot a y1 here. Yeah. Okay, so that was the y double prime, a plus p times y prime. So that would be, let's say, p times y2 prime here. Okay. And then finally, I guess, yeah, q times y. So q times y y2. Okay. And that has to equal to 0. Okay. So what we're going to do is collect terms according to powers of u. The order of the derivatives of u. In other words, I'm going to take the u double prime term. Okay. Then I'm going to collect the u prime terms. Go ahead and factor the u prime out. And we'll gather the u terms together as well, factoring out the u. Now, since y1 is a solution to the homogeneous differential equation, we know that this will reduce to 0. Okay. So the last term there goes away. And so here we have a second order differential equation for u, but there is no u term, right? So this means we can reduce the order by saying by letting, let's say, w equal to u prime, so that w prime is u double prime, and you can substitute. So u double prime becomes w prime, and u prime just becomes w. So you've effectively reduced the order of this differential equation by 1 degree. And this is, you have to recall that y1 is known, right? So this is in fact a separable differential equation where I'm going to write w prime is the derivative of w with respect to x. Move this term to the right-hand side. And separate the variables. I'll have w on one side, the w's on one side, and this function of x Again, remember, y1 is a known function of x. So divide by y1, function of x. So we've separated the variables, and let me go ahead and simplify the right-hand side by dividing both terms in the numerator by y1. Wait a minute, where did I get the 2p from? Okay, so there's no 2 over here. Okay. And we anti-differentiate both sides now. Again, I'm just going to ignore the constant of integration since we're looking for some factor u that works here. So to anti-differentiate y prime over y, you can see by a simple substitution that this is just log of y1, right? Differentiate this to confirm. So you get -2 log of y1 minus the antiderivative of p dx. We exponentiate here. So we get w is, in here we can take advantage of properties of logs and exponentials. Okay. So we get the w is, let's see, y1 to the -2, or just y1 squared in the denominator, if you will. Okay. So then we back substitute. We know that w is really u prime. So we recover u by anti-differentiating, and there we go. We get a u that works. Okay, so that was the formula for u in the reduction of order formula. Okay, so let's do another one like this, and maybe this time we'll maybe use the formula really quickly, but also go through this procedure with the example as well. So, example. Okay, let me just erase that. Ugh. I can't figure these whiteboards out sometimes. Okay. So, so here's a differential equation that doesn't have constant coefficients multiplying y and its derivatives. It's homogeneous, but not constant coefficients. So I'm going to first write this in the conventional form for using the reduction of order formula. So I'm going to have to divide everything by x squared. Here I'm just going to assume that x is diff. Okay. Okay. We identify p of x as the thing that multiplies y prime, so that's going to be 1 over x. Oh, and then I'm going to tell you that one of the solutions is, so a given solution is this equation is x squared. You can confirm that this actually is the solution to the differential equation. So we're going to assume a solution, y2, that is equal to some function of x times y1. And we saw a formula, we derived the formula for u. So we have p of x is 1 over x. y1 is x squared, so x squared squared in the denominator. And we compute u. Again, I'm just ignoring the constants of integration. There, I'm just taking advantage of properties of logs. And of course, exponential and log are inverses of one another, so up to a constant of integration. Okay, so I'm gonna, in fact, I need multiple of this work, so I'm just gonna assume that since this is proportional to x to the negative 4, I'll just assume that's my u, not that it matters. So y2 then apparently is u of x, I'm just gonna use that, times y1, which is x squared. So you get x to the negative 2. Okay, so this indeed is a fundamental solution set to the original differential equation. And the general solution then to this differential equation is just some combination of C1 and C2. Of Y1 and Y2, sorry. Okay. So that's our general solution. Okay. And I said that we might go through the procedure that, that kind of parrots the derivation of that formula for you, but I think for the sake of time, I'll skip that. Okay, so second topic is this topic of just working with second order ordinary differential equations where the coefficients are constant. And the equation, so ODE, with constant coefficients. And for right now, we just want to talk about homogeneous. Sorry, homogeneous. Okay, so that's going to be something like we already seen, like y double prime minus 6y prime plus 9y equals 0. So the constant coefficients come from, not the things multiplying y and its derivatives being constants, like 1 times y prime, negative 6 times y y prime, and then 9 times y. The homogeneous, of course, is referring to the right-hand side being 0. All right, so I'll write this in kind of generic. So A, B, and C here are real numbers, say. Okay, and what we're going to do is assume, again, like we do many times in, there's an umlaut somewhere there. Okay, we assume that there's a form for the, something will be a solution, and we're going to assume it's the form exponential times r, an unknown number. It's unknown right now, which could be real number or even complex number. So in general, it's a complex number. You know, reals being a subset of the complex numbers. Now let's see how this assumption helps us find a general solution to this homogeneous equation. So of course, if you want to find the r that works, that gives you a solution to the equation, you would differentiate y once, and then x is the independent variable, twice, and then you plug y and its derivatives into the equation. So we get a times y prime, y double prime, sorry, plus b times y prime plus c times y, and that's equal to 0. So notice that that exponential, that e to the rx, is a common factor. Which we can factor out. And it's non-zero. So we'll just divide by it to get a polynomial of degree 2. And now how would you, so of course, this times that is 0. And the exponential is not 0. So this polynomial part must be. If you want to, if indeed this is a valid solution, right? The polynomial part must be 0. So we can use the quadratic equation to solve for r. And we find roots of this polynomial. So this is called the characteristic polynomial of your differential equation. And so once you have your roots, okay, you kind of know what the solutions are, right? Because you assume that that's a solution. So if you know what r is, you have a solution. And there's some complications because you could have, for example, repeated roots, right? Or we could have complex roots. So we have to consider those cases. So let's consider the cases for the roots of this characteristic polynomial. Okay, so the cases, just delete all that. So the cases are going to be 3 cases, right? So there are 3 cases for the characteristic polynomial, or corresponding to our differential equation. Okay, first case is that you could have, so case one is you have real distinct roots. So your roots of the polynomial are real numbers, so R1 and R2 are real numbers, and furthermore they're not equal, so they're distinct. Okay, in which case the two independent solutions to your second order differential equation, as we assumed, was e to the r, so R1 times x, and e to the R2x. So that's your fundamental solution set there. And so your general solution to this homogeneous differential equation is just a linear combination of those two functions of the fundamental solution set. Okay, so that's not r of x, that's r times x. Come on. Ah, jeez. All right. So general solution. This is our fundamental solution set. And I will provide an example of this case. I think, if I can find it. Well, there you go. Sorry about that. So this is an example of case one. So we have y double prime plus 4y prime plus 2y prime minus 3y equals 0. So second order homogeneous constant coefficients for y and its derivatives. So I know that there are solutions in the form e to the rx, and we know that to find r we have to find the roots of the characteristic polynomial, where the r squared term corresponds to the y double prime, the r term corresponds to the y prime, and the constant terms corresponds to the y term. Okay, so we'll just, well, you can use quadratic formula here. I can see that this factors nicely. Okay, so the two roots are -3 and +1. So I know that the fundamental solution set here would be e to the √1 times x, and then the second independent solution will be e to the √2 times x. So my general solution is a combination of the functions in my fundamental solution set. Okay, and you can check that those work. Okay. Now, that's case one, and what made it fairly simple is that well, we had real roots and they were different, they were distinct, right? And that gave us, you can prove using the Vronsky that would, if you have distinct roots, then these are independent functions, right? The Vronsky will not be equal to 0, the number line, in fact. So a complication, of course, will be that we have real roots, but they're repeated, right? It's like a root of multiplicity 2. So let's deal with that case. So case 2 is a real root that's repeated or has multiplicity 2. So you have root 1 and root 2 are equal, if you will, and they're real numbers. So then I can tell you that the solution is e to the root, let's just call that root r, x. And the second solution is the same thing, but see, that would be the problem, right? If these wouldn't be independent, but if you multiply that by x, this will also be a solution and will be linearly independent from the first one. Okay. And you can derive this by using, can be derived using reduction of order. So in fact, it's very similar to the first example I did in this review. So you don't need to derive that, but just know that if you wanted to, you can actually prove that this is another solution, given that we know the first one. And it's by using reduction of order. Okay. So your general solution then would be a combination of this. Okay, so we'll do an example of this case. So it is exactly the example that we started with in the review. So okay. Homogeneous constant coefficients. We write down the characteristic polynomial, and we see that you can easily factor this, and we see that 3 is a root, but it's repeated, so multiplicity 2. So I know that my fundamental solution set would be e to the root times x, and the second solution is e to the 3x, but because it needs to be independent, you get that if you multiply that by x, you get another independent solution. Your general solution is just a combination of the functions in your fundamental solution set. Okay. So that's our solution there. All right, so the third case is where, right, we did real roots that are either distinct or repeated. So of course, when we have a quadratic polynomial, the roots could be complex. Okay. So we're going to do the third case, case 3, where the roots are complex roots, and they for a quadratic, these complex roots always come in conjugate pairs. Complex conjugate pairs, right? Or I guess that's singular, a pair. Complex. So your roots are going to be in the form the first root is going to be like alpha plus I beta. If you call this is called the real part of the complex number, and the real number multiplying the imaginary I is called the complex part of the real number. So the complex part is not a complex thing, it's a real number. And the second root will have to necessarily be a conjugate if you're dealing with a quadratic. So alpha minus I beta. Okay, so sometimes you can just write this as alpha plus or minus I beta. Okay. Then the solutions, without deriving, using Euler's identity, you can derive that the fundamental solution set is going to be, the first function is like e to the alpha x. So alpha is the real part, and then times, let's say sine, then, sorry, I'm going to use cosine just because I'm stubborn. So cosine and then beta, the imaginary part, times x, the independent variable. Okay. And the second independent solution is going to be this exponential. We have the real part times x, and then the sine instead of cosine, then the imaginary part beta times x. Okay, that's your fundamental solution set. Your general solution is just a combination of those. Okay, so we'll look at an example of, or maybe even two examples of this case. So consider this homogeneous differential equation with constant coefficients. We're going to write down the characteristic polynomial, and I'm just going to use the quadratic formula to find the roots. So 80 and 36 is 160. So that's the square root of a negative 100. So that's negative 4 plus or minus I-10. Not the highway in Texas, but okay. Okay. So our roots, indeed, our roots are complex conjugates. The real part is negative 2, and plus or minus I, and the imaginary part, say, is 5. So according to what we wrote above, the fundamental solution set should be e to the alpha x times cosine of beta, so that's 5, times x. And then for the other linearly independent solution, it's e to the alpha x times sine of beta x. Okay, so that's our fundamental solution set. Okay, and so be careful, of course, on your root could be purely imaginary. So maybe the real part is 0. So if you have the real part being 0, then your solution, your fundamental solution set would have the exponential part would just be e to the 0, so 1, so that would go away. right? So if we had instead y double prime plus y equals 0, okay. This whiteboard can be very, very laggy. Microsoft. Yeah. So write down the characters to polynomial. Notice there's no y prime term, so it's just a constant 1. So r could be plus or minus the square root of negative 1. So r is plus or minus I. So here the real part is 0 and the imaginary part is 1, if you will. So our solutions the exponential will become 1, so it goes away. So you get cosine of x, 1 times x, and sine of x. Okay. So when a purely imaginary root, so the real part is 0, the exponential stuff goes away in the sense of being 1. Okay, so I don't know if I'll make this too small, but there were 3 cases. Yeah, that's too small. But there were 3 cases. Okay. So okay. So now let's move on to what would happen if you had a second order differential equation with constant coefficients, but the right-hand side were not 0. So it's a non-homogeneous differential equation. So we're going to move on. And this is where it might get complicated. I might not cover method of undetermined coefficients in this video. Okay, probably won't have time. But we're going to look at second order ordinary differential equations, constant coefficients, that are also non-homogeneous this time. Okay. So an example of this might be right, and that's equal, and since we want non-homogeneous, that means the right-hand side is no longer to 0. It's just some function of x. G of x is non-zero. Okay, so what I'm going to outline the procedure for solving this non-homogeneous equation. So number 1, you find a general solution to the homogeneous version of this problem. Okay. So we're going to write that as, let's say, y sub h for homogeneous, and you're going to get a combination of two independent functions that solve the homogeneous differential equation, not the original. Okay. Number two, you're going to find a particular solution to the original. So to the non-homogeneous differential equation, the right-hand side is not zero. And so we'll write that as yp. And it's some function of x, right? And the main focus of what I want to go over is actually how to find this particular solution. But let's assume we found it, okay, whatever the method is, right? Let's say we assume we found it. Then the general solution to the original equation is going to be the homogeneous part plus the particular solution. And so this is a linear differential equation, and you've probably taken linear algebra, and so you've probably seen this before when you have the matrix equation AX equals B. So matrix multiplication is a linear operation on X. And if you wanted to find a general solution to this equation, you knew that you would find a solution to the equation AX equals 0. So you find a homogeneous solution to the homogeneous equation, and then you find a particular solution, and then all solutions then can be written as the homogeneous part plus a particular solution. Okay, so it's very analogous to that, except here the linear operator is not a matrix, but rather it's the differential operator. Okay. So you have the homogeneous part, and the coefficients here make this a general solution plus the particular part. Okay, and number 4. So number 4 would be if you had initial conditions. So for a second order differential equation, we would have two initial conditions, say. Okay. So we have y at an initial value of x is equal to some initial value for y prime, so you have a condition for the derivative as well. There's some value. So for second order, we would need two initial conditions. If you have these initial conditions, you can now, only after finding the most general solution to the non-homogeneous equation, only now would you solve for the coefficients. Using those initial conditions. So I guess what I'm trying to say is, when you find your homogeneous solution, and you have initial conditions, you don't solve for those coefficients at that point. You wait until you find your particular solution here. And only then, once you have the full general solution to the non-homogeneous equation, only then would you solve for the coefficients using your initial conditions. Okay. All right, but what we're after really in this part of the review is a method for finding a particular solution. Okay. So this method we're going to look at is called the method of undetermined coefficients. Okay. So method of undetermined coefficients. It's a method to find a particular solution to a non-homogeneous equation. Okay. Okay, and this method is restricted to only special cases where we have. All right. So it's restricted to you have constant coefficients, and the right-hand side, RHS, right-hand side of the equation has to be of a special form. It has to be in the form some polynomial times some simple exponential, so like e to the x, but maybe not e to the x squared. And then times the sine or cosine. So no tangent or anything, right? So you have some polynomial of a degree. I mean, yeah, you know what a polynomial looks like. A simple exponential, so that might be something like e to the number times x. That's what I mean by simple. And then sine or cosine of some number times x. Again, simple. So it's kind of related to a simple exponential. You need a simple sine or cosine. Okay. So you're going to have constant coefficients, and it's non-homogeneous, non-homogeneous. So the right-hand side will be, we're restricting method of undetermined coefficients to the case of polynomial, simple exponential, and then sine or cosine. Okay. All right. So method of undetermined coefficients says that we're going to assume that a particular solution, like, okay, we already know how to find the homogeneous solution, right? If we were just to cover up the, oh, it's an infinite ruler, I can't cover that up. Okay. If we were to cover up the right-hand side, right, and say that's 0, then we have a homogeneous constant coefficient differential equation, and we know how to find a solution to that using characteristic polynomial. But so the next step would be to find a particular solution. Okay. And you're going to assume that the particular solution, yp, is equal to some generic form, I will go into what that means, of the right-hand side. G of x. Okay? And then times, possibly, you multiply this generic form by x to some integer power, x to the n, where n is the smallest. That's important integer. So that each term, that's important. So every single term in the particular solution is independent. So like not a like term from everything in the fundamental solution set. So every function in the fundamental solution set. So that's a mouthful. It'll be easier once we do an example. Okay, so instead of going through the example, since out of time, I'll just save this for next time. Okay. So the next video should be about method of undetermined coefficients.